So this is week 9 of the Applied Thermodynamics course. So this is the ending session on the gas power cycles. So from next week we will be looking at refrigeration and psychrometrics and so on. So in the previous week we saw about a Brayton cycle, an open cycle and a closed cycle, and the variations which we can apply to the Brayton cycle to improve its efficiency. So before moving on to this session, I'll just give a recap on this Brayton cycle, because the coming this week is also related to what we did in the previous covered in the previous week. So Brayton cycle consists of in open cycle 3 components, major components. One is the compressor, your combustion chamber, and then your expander or turbine. So you take fluid from inlet to the compressor, either in ambient or compressed gas. So you compress it, and then you add some fuel and burn it, and then after that in the combustion chamber that is a heat addition, and then you are expanding in the turbine and it's producing work. So similar concepts in the use in aircrafts. So aircrafts, you have various types of engines. So the major one is the turbo prop, then turbojet, and then ramjet. So turboprop, you have a propeller at the start, and then you have a compressor, and then combustion chamber, and then an expander. And basically, because of the velocity of fluid which is coming out, that drives, based on Newton's third law of motion, drives the aircraft. So in turboprop, this propeller and the exit velocity both aids in the process of the aircraft motion, and this propeller is driven by the propulsor, and the compressor is driven by the turbine where the work is generated. And to improve this efficiency of this turboprop, you can add a diffuser at the start, and removing that propeller, it will become turbojet. So that's one variation which can be applied to the turboprop engine. And the turboprop is good for pickups, so high torque and this thing for lift which can get from the ground level. But when the velocity increases, the efficiency of this turboprop decreases at higher velocities when you are going near the sonic velocity and above. But at lower velocity, with respect to velocity, it increase, and after a point it will start decreasing. In case of turbojet engine, what happens is you have a diffuser at the start, and then whatever air is coming, and at the entrance, after diffuser you have a compressor. So this velocity is brought down, and then you are compressing it, and the process again remains same. So this is a turbojet. So initial the bringing down of velocity and the pressure increase is called a ram effect. So that is what is used in a ramjet engine. So this is to give you a brief idea on the engines, aircraft engines. So we'll see numericals on this and MCQs on this. So starting with, we have first one, a jet engine works on the principle of conservation of dash: A, mass; B, discharge; C, momentum; and D, energy. So the first question is, a jet engine works on the principle of conservation of dash. Answers: A, mass; B, discharge; C, momentum; and D, energy. So jet engine works on the principle of conservation of momentum. So answer is option C, momentum. So moving on to the next question. In working condition of turbojet engine, velocity of air entering the engine is dash, then the velocity of exhaust gases leaving the engine. A, lower; B, higher; C, equal to; and C, cannot say. So they are saying in the turbojet engine, what is the velocity of air entering the engine is compared to the exhaust gases leaving. So answer is A, lower. So that's why in conservation of energy, if you your mass, the change difference is what is causing that to drive. So your exhaust is at a higher velocity compared to what is there in the inlet. So the answer is option A, lower. So the next question is, through the intake of an aircraft, the process of converting the kinetic energy of the entering air into the pressure rise is known as ram effect. It's a true or false question, so answer is true or false. So this I have already explained in the case of a ramjet engine what happens. So if your aircraft is moving, it is moving at some velocity. So the air which is coming in, so the relative velocity for the air is also the same. So that velocity, you have a diffuser at the inlet, so you're converting that velocity into a pressure rise. So you're reducing that velocity, and because of that there's an increase in pressure. So this effect is called as a ram effect. So the question also says the same. Through the intake of an aircraft, the process of converting the kinetic energy. So kinetic energy is you have process some velocity in the kinetic energy that is getting converted into pressure. So answer is true. The next is, the air standard cycle for a turbojet engine is based on dash. Answer A, reversed Brayton cycle; B, diesel cycle; C, Brayton cycle; and D, Joule cycle. So this is answer C, Brayton cycle. So also see the components also is same. You have a compressor chamber, and your expander. So this is what we are having in a Brayton cycle. And so reverse Brayton cycle is used in refrigeration application. Also in aircrafts you can use that. So air standard refrigerant cycle and diesel cycle, which we have already seen. Next is, afterburners in aircraft engines are used to decrease the thrust of a turbojet engine. So A, true, and B, false. So answer is false. So we see an afterburner is additional combustion component. So used on some jet engines, its purpose is to use to increase thrust. The afterburning process injects additional fuel into the combustion after the turbine, reheating the exhaust gas. So you are increasing energy of the fuel after the expander. So you are reheating the fuel, and this is mainly is done to increase the thrust. Thrust is the force which you get because of the change in velocity. So this increases in enthalpy is converted into velocity. so that gives you additional thrust. So these afterburners are used to increase in thrust, not to decrease the thrust. So answer is option B, false. So the next one is the turbojet engines mainly employ axial flow compressors. Option A, true, and B, false. So it's asked what type of compressor is being used. So answer is true. So it's an axial flow compressor. So if you see in aircraft, you have on the wings, so the flow is to, the direction of axis. So these are axial flow compressors, and your exhaust is also in axial. So it's an axial flow compressor. Then the next question is isentropic efficiency defined in terms of dash and ram efficiency expressed in terms of dash respectively are two methods by which the efficiency of intake system are analyzed in a turbojet engine. So we know how to this, calculate this isentropic efficiency. We generally use the enthalpies, or in case if you assume idle gas, it becomes the ratio between temperature. So defined in terms of temperature rise, and then ram efficiency, we know ram effect. What is ram effect? So your kinetic energy is converting that energy is converted to a rise in pressure. So that is called as a ram effect. So this efficiency is calculated using the ram efficiency. So this is calculated based on the pressure rise. So answer is option C, temperature rise and pressure rise. So next is propulsive efficiency of a jet engine dash with an increase in aircraft velocity. So answer is A decreases, B increases, C remains constant, dash none of these. So answer is A increases. So propulsive efficiency of a jet engine increases with an increase in aircraft velocity. So this is how the propulsive efficiency is defined. Is thrust power divided by propulsive power. So next is which of the aircraft engines do not use compressor? A, ramjet engine, B, turbojet engine, C, turboprop engine, D, turbofan engine. So we have discussed the effect called ram effect. So we know the velocity is converted into rise in pressure. So ramjet engine also works in this principle. So the answer is A, ramjet engine. So you basically use the ram effect to compress the fluid and not the compressor. So answer is A, ramjet engine. So next question is, in jet engines, the gases expand to ambient pressure in a jet nozzle. A, true, B, false. So what said? So you have an engine, you are taking, it's coming, the air is coming in at some velocity. So if you have a wrap effect, if there is a rise in pressure, then you are compressing it. Then there is heat addition by fuel injection and combustion. Then you are expanding it. So this expansion you are doing basically to run the compressor. So after that, it passes through a nozzle. So it's called a jet nozzle. So where there another expansion happens. So this increases the velocity. So if you see, it's true because at the end of the nozzle outside it's the ambient, so it's expand till ambient. So answer is really true. So now we have a problem here. So air enters a turbojet engine at 320 meters per second at a rate of 30 kg per second and exits at 650 meters per second. So relative to the aircraft, the thrust developed by the engine is, you have to find out the thrust. So here we have a turbojet engine. So this turbojet engine, air is coming in as 320 meters per second, and going out at 650 meters per second. So you see there is a clear difference in the velocity. So inlet is at 320 and outlet is at 650, and you know the mass flow rate through the engine. So what is the thrust developed? So this is the difference between the velocity. So the change in momentum is what is giving the thrust. So m is the rate dm by dt into v2 minus v1. So m is 30 kg per second into the change difference in velocity, which is 650 minus 320, which comes out to be 9900 Newton or 9.9 kilonewton. Goes to 10 kilonewton in the problem. So answer is option B, 10 kilonewton. So next so we'll move on to problems now. So we have a turbojet engine which consumes air at the rate of 60.2 kg per second when flying at a speed of 1000 km per hour. So calculate exit velocity of the jet when the enthalpy change for the nozzle is 230 kJ per kg and velocity coefficient is 0.96. To fuel flow rate in kg per second when air fuel ratio is 70:1. Third is thrust specific fuel consumption. Fourth is thermal efficiency of the plant when the combustion efficiency is 92% and the calorific value of the fuel used is 42,000 kJ per kg. Fifth is propulsive power. Sixth is propulsive efficiency, and seventh is overall efficiency. So we need to find all this. So we'll go one by one. So starting, we'll focus on what is given. So we have a turbojet engine, and it says that it consumes air at rate of 60.2 kg per second. So the air flow through the turbojet engine is 60.2 kg per second, and this is flying at a speed of 1000 km per hour. So we know the velocity. So we now need to find out. First one is velocity coefficient is given, and they also say that exit velocity of the jet when the enthalpy change for the nozzle is 230 kJ per kg. So velocity coefficient given and the enthalpy change across the nozzle is given. So we'll list out what is known. So rate of air combustion n dot A 60.2 kg per second, enthalpy change across nozzle is 230 kJ per kg. Then velocity coefficient is Z is 0.96, air fuel ratio is 70:1, combustion efficiency 92%, calorific value is given, and aircraft velocity is 1000 km per hour. So converting that into meters per second, so 1000 into kilometer multiplied by 1000 divided by R is 60/60. So it will come out to be 277.8 meters per second. So that is my aircraft velocity. Now the jet velocity or of the exit stream. So exit velocity of jet is if you apply first law for control volume across the nozzle. So you have there will be dE CV by dt plus your enthalpy of exit minus enthalpy of inlet equals Q minus W. So my assuming this is in steady state, so the E C by dt will be 0, and there is no heat transfer, there is no work, so Q minus W is 0 for the nozzle. So it will be enthalpy plus velocity, my kinetic energy equals enthalpy at exit plus kinetic energy. So the inlet velocity, if we assume it's negligible for the nozzle, then exit velocity will become my phase of root of 2 into delta h. So that's what is written here. So the velocity is root of 2 into delta h, so into 1000 to convert kilojoule into joules, and z is my velocity coefficient. It's like the efficiency of the nozzle. So multiplying velocity coefficient into root 2 delta h. So delta h across the nozzle is given as 230 kilojoule per kg. Substituting that, z is 0.96 into root of 2 into 230 into 1000. So this comes out to be 651 meters per second. So my exit velocity of jet is 651 meters per second. Next is I need to find out fuel flow rate. So rate of fuel consumption is rate of air consumption divided by air fuel ratio. So I know rate of air consumption, which is given as 60.2. So 60.2 divided by 70 will give 0.86 kg per second. So that is the rate of fuel which is being consumed. Next is thrust specific fuel consumption. So this is just like what we did in internal combustion engines. So indicate power specific fuel consumption, brake power specific fuel consumption, just like that. This is thrust specific fuel consumption. That is your mass fuel used divided by the thrust generated, or you can say per kilonewton. There in production kilowatts, so here per kilonewton of work, how much mass fuel is required. So thrust specific fuel consumption is fuel consumption divided by thrust. So we need to find out first thrust. The thrust produced is similar to what we saw in the previous problem, your mass into change in velocity. So mass flow rate is I know, which is 60.2 into my outlet velocity of the jet I have found out, it is 651, and inlet is the aircraft velocity, so minus 277.8. So this comes out to be 22466.6 Newton, or close to 22.5 kilonewton. So thrust specific fuel consumption is, I know fuel consumption is 0.86, so divide by thrust, which is 22466.6, it comes out to be 3.828 to 10 power minus 5 kg per newton of thrust per second. So next is we need to find out the thermal efficiency. So thermal efficiency is nothing but work output divided by heat supplied. So thermal efficiency will become my gain in kinetic energy per kg of air divided by heat supplied by fuel per kg of air. So this becomes my total mass flow rate per kg of air is 1 plus mf by a ma into my velocity change. So v square exit by 2 minus V inlet by 2, square inlet by 2. So that is the change in kinetic energy, divided by mf by ma into calorific value. So substituting it here, so 1 plus 1 by 70, so 1 by 70 will be very small, so neglecting, so 1 into 651 square minus 277.8 square, so that is the velocity change, divided by 2, first kinetic energy is v square by 2, mv square by 2, so into mf by ma is 1 by 70, the fuel air ratio, into calorific value is 42,000 kilojoule per kg is given, then into your combustion efficiency is 92%, so 0.92 into 1000, so this comes out to be 0.3139 or 31.39%. So the thermal efficiency of this engine is 31.39%. So next is the propulsive power. So propulsive power is again what we found out is mass of air, the kinetic energy of air, change in kinetic energy of air. So mass of air into the exit stream velocity square by 2 minus inlet stream velocity square by 2. So this becomes mass of air is 60.2 kg per second into velocity 651 square minus 277.8 square by 2 and divide by 1000 to convert it into kilowatt. So this comes out to be 10,433.5 kilowatt. So that is the propulsive power generated by the turbojet engine. Next is propulsive efficiency. So propulsive efficiency is nothing but thrust power divided by propulsive power. So thrust power we have already calculated. So mass into your difference in velocity Cj minus Ca divided by your propulsive power is your change in kinetic energy. So change in momentum divided by change in kinetic energy. So if you simplify it, it will come out to be 2 times your inlet velocity or aircraft velocity divided by inlet into inlet plus aircraft. So this is the simplified expression for the propulsive efficiency. So propulsive efficiency becomes substituting the velocities. So 2 into 277.8 divided by 651 plus 277.8. This comes out to be 0.598 or 59.8%. So that is the propulsive efficiency. Next is we need to find out the overall efficiency. So that is nothing but your thrust work divided by heat supplied by fuel. So thrust work in this case is Cj minus Ca into Ca, this is per kg of air, divided by my combustion value, mass of fuel into calorific value into combustion efficiency. Substituting here, this becomes thrust work is 651 minus 277.8 into 277.8 divided by 1 by 70, which is fuel air ratio, into calorific value into 0.92 combustion efficiency into 1000 to convert into joules. So this comes out to be 0.1878 or 18.78%. on turbojet engine. But previously we didn't assume there is a ram effect. So, but here we are assuming there is a ram effect. So, because there is a diffuser at the front, so to solve for that additionally. So what we have is a turbojet engine which travels at 216 meters per second in air at 0.78 bar and minus 7.2 degrees Celsius. So this is your ambient condition for the turbojet engine. So that is in my inlet pressure and temperature. So I know that first initially the turbojet engine is traveling, the aircraft is traveling at 216 meters per second, and the air which is coming in is coming at 0.78 bar and minus 7.2 degrees Celsius. So air first enters the diffuser, in which it is brought to rest relative to the unit, and it is then compressed in a compressor through a pressure ratio of 5.8 and fed to a turbine at 1110 degrees Celsius. The gases expand through the turbine and then through the nozzle to atmospheric pressure, so that is 0.78 bar. So the efficiency of diffuser, nozzle and compressor are each 90%. The efficiency of the turbine is 80%. Pressure drop in the combustion chamber is 0.168 bar. Determine 1. Air fuel ratio. 2. Specific thrust of the unit. 3. Total thrust if the inlet cross section of the diffuser is 0.12 meters square. Assume calorific value of the fuel as 44,150 kilojoule per kg of fuel. So actually what all we have to find? We have to find air fuel ratio, we need to find specific thrust and total thrust. So what is given? Aircraft velocity is given, which is 216 meters per second. I know inlet pressure and temperature, and I know efficiency of each of the component. So diffuser is nozzle and compressor is 90% and turbine is 80%. They have also said there is a pressure drop across the combustion chamber, which is 0.168 bar. I know the pressure ratio in compressor and the turbine temperature, inlet temperature to the turbine. So this all is given, and also diffuser cross section area is given. So that is all listed here. So you see speed of the aircraft 216 meters per second. Intake air temperature is 265.8 Kelvin. So converting degrees Celsius to Kelvin, minus 7.2 plus 273 is 265.8. The intake air is 0.78. Then pressure ratio in the compressor is 5.8. So temperature of the gas entering the turbine is 1110 plus 273, which is 1383 Kelvin, and pressure drop in combustion chamber is 0.168. So, and my efficiency is all given. So nozzle, diffuser and compressor efficiency is 90% and turbine is 90%, and calorific value of fuel. So this is how the process looks. So 1 to 2, ideally it's an isentropic compression, the ram effect. So 1 to 2, there is a velocity is converted into increase in pressure. So these are isobars, and then you are from the diffuser, your then actual process is 1 to 2 dash. So 1 to 2 is the ideal one. So actually it's 1 to 2 dash. So from 2 dash compressor ideal is 2 to 3, 2 dash to 3, but the process follows 2 dash to 3 dash because compressor efficiency is again given. From 3 dash to 4, you are in the combustion chamber where your heat is added, or this combustion rises its pressure and temperature. Similarly, rise is temperature, not pressure, so it's a constant pressure process. But here there is a pressure drop, though this is shown as constant pressure, so there is a slight pressure drop here across the combustion chamber. So 4 will be at lower pressure compared to the inlet 3 dash, and that temperature is given 1383. Then 4 to 5 is in turbine, so actual is isentropic 4 to 5, but it doesn't follow that, so it will be 4 5 dash. Then 5 dash to 6 is in the nozzle, so again isentropic, it's not isentropic actually, so 5 dash to 6 dash. So this is the whole process, and this is expanding to till the ambient temperature condition, so ambient pressure, not temperature, ambient pressure. So you see 1 and 6 lies in the same isobar, so because inlet is at 0.78 and exit is also at 0.78. So first is we need to find out air fuel ratio. So we assume that it's an ideal diffuser, and if we apply an energy balance across the steady flow energy equation across the diffuser, assuming so in the diffuser, if you see there is no heat transfer, there is no work transfer, we are just assuming the diffuser and you are applying the steady flow energy equation. So there is no heat transfer, there is no work transfer, and whatever inlet is coming is going out, there is nothing getting stored, so the control volume energy change is also 0, so it's a steady process. So, and assuming that inlet velocity, exit velocity is relatively 0 to the aircraft, so exit velocity becomes 0, so so this becomes so the mass coming in and mass going out is same, so the steady flow energy equation becomes mass, okay, it's cancelled out, so enthalpy equals enthalpy in plus kinetic energy in equals enthalpy out. So H2 is the enthalpy at exit equals H1 plus Ca square by 2, this aircraft velocity, the inlet velocity by 2. So can write this as H2 minus H1 equals Ca square by 2, or if we assume your Cp is constant and doesn't vary with pressure, so it becomes T2 minus T1 equals Ca square by 2 Cp. So from this we can find out temperature at the diffuser exit. So we know inlet temperature, so inlet temperature is 265.8, so 265.8 plus velocity square 2 and square 6 square by 2 into the Cp of air is 1.005 kilojoule per kg Kelvin, so we are converting into joule, so multiply by 1000, so this becomes 289 Kelvin. So this is for an ideal diffuser, but our diffuser is not ideal, so it has an efficiency of 90%. So the diffuser efficiency is defined as H2 minus H1, which is the actual enthalpy change, divided by H2 dash minus H1. So H2 dash minus H1 will become H2 minus H1 by your diffuser efficiency. So H2 dash will be H1 plus your ideal enthalpy change divided diffuser efficiency. So this will be, if you see, ideal enthalpy change is equal to the velocity square by 2. So H2 minus H1 is Ca square by 2. So here there is a 2 times of diffuser efficiency. So H1 plus Ca square divided by 2 into diffuser efficiency. The 2 is missing, so that should be a 2 here. So converting this into temperature, So we have to divide it by Cp. So T2 dash will be T1 plus Ca square divided by 2 Cp into diffuser efficiency. So substituting this, so inlet temperature is 265.8 plus 216 square divided by 2 into 1.005 into 1000 into 0.9. So this becomes 291.6 Kelvin. So this is the actual temperature at the exit of the diffuser. So now we need to find out the rise in pressure. So now we know temperatures, the isentropic, assuming it's across the diffuser, is an isentropic process. So we know the two temperatures, so we can find out pressure, and we know inlet pressure. So for an isentropic isentropic process, T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. So we know the temperature, so T2 is 289 divided by 265.8 equals P2 by your inlet pressure is the ambient pressure, so 0.78 raised to power 1.4 minus 1 by 1.4, gamma for air is 1.4. So this comes out to be 1.087 raised to power 3.5, that is 1.4 divided by 0.4 is 3.5, so equals P2 by 0.78. So P2 is 1.0044 bar. So this is the, because of the RAM effect, your pressure is increased from 0.78 bar to 1.044 bar, and your temperature is increased from 265.8 to 291.6 Kelvin. So pressure we are getting from the isentropic process, and the temperature also doing an energy balance, and then using an efficiency formula we have found out the temperature. Next is, again if you see across the compressor, the pressure ratio is given. So I know the compressor inlet temperature now, so that is the exit temperature of the diffuser. So I can estimate the exit temperature of the compressor. So T3 by T2 dash is a pressure ratio raised to power gamma minus 1 by gamma, and pressure ratio is 5.8. So this becomes T3 by T2 dash is 1.652. So T3 becomes 291.6, which is the diffuser outlet temperature, into 1.652. So this becomes 481.7 Kelvin. So again now compressor efficiency, applying compressor efficiency. So T3 minus T2 dash, which is the actual, so ideal divided by actual. So diffuser and compressor will have the same formula, it's ideal divided by actual, and work producing nozzle and this thing will be actual divided by ideal. So here T3 minus T2 dash divided by T3 dash, which is the actual compressor exit temperature, minus T2 dash. So this comes from the enthalpy form. So it's actually enthalpy change in ideal divided by enthalpy change in the actual. So T3 dash will be equals T2 dash plus T3 minus T2 dash divided by the compressor efficiency. So T2 dash we have found out, which is 291.6, so diffuser outlet, plus my T3 is 481.7, which we have found out here, minus 291.6 divided by 0.9, so this becomes 502.8 Kelvin. So now to assume the Cp as constant as Cp, so heat supplied will be the change in my enthalpy across the combustion chamber. So the combustion chamber inlet is at temperature T3 dash and exit is at temperature T4, and also the inlet so doing an energy balance across the combustion chamber. So the exit is at Ma plus Mf, so that is the air plus fuel carried into Cp of that mixture into T4 minus the air which is coming in, so Ma into Cp into T3 dash this will be equal to uh, the energy provided by the combustion, so mass of fuel into calorific value. So here combustion efficiency is not given, so we'll assume that it is 100%. The combustion efficiency is 100%. So whatever is being combusted, energy produced is taken by the air. So now, so Ma into CpT4 plus Mf into CpT4, so minus Ma into CpT3 dash equals Mf into C. So we are just expanding the bracket and taking all air terms and fuel terms together. So Ma Cp into T4 minus T3 dash equals Mf into calorific value minus Cp into T4. So now we get the air fuel ratio, Ma by Mf will be your calorific value minus Cp of air into temperature at the turbine inlet divided by your enthalpy change per kg of air. So Cp into T4 minus T3 dash. So this becomes, so we are substituting, calorific value is 44150 minus your Cp of air is 1.005 into 1383 is the temperature to the turbine inlet. So that is your combustion chamber exit, divided by 1.005 into 1383 minus your inlet to the combustion chamber is at 502.8, which you have calculated from the compressor. So the compressor exit was 502.8. So substituting that, we get 48.34. So that is the air fuel ratio. So air fuel ratio is 48.34. Next is we need to find out the specific thrust of the unit. So now what is given is in the combustion chamber there is a pressure drop of 0.168 bar. So I have to find out the exit pressure of the combustion chamber or inlet pressure to the turbine is P4 given by P3 minus 0.168. So I know P3, the pressure ratio across compressor is 5.8, and I have found out the exit of the diffuser conditions. So pressure was 1.044 there. So that into pressure ratio will give me the pressure at the exit of the compressor. So 5.8 into 1.044. So that is the exit pressure of the compressor or the inlet pressure to the combustion chamber minus the pressure drop. So 0.168 gives me 5.88 bar. So that is the pressure to the turbine. Now assuming that the turbine drives the compressor only, so there is no other auxiliary accessories which is there. So the turbine is generating only that much amount of work to drive the compressor. So the work done in the compression will be equal to the work developed in the turbine. So work provided to the compressor is equal to the work generated in the turbine. So there will be change in enthalpy will be same. So because the mass flow is same, I can straight away write as Cp T3 dash minus Q dash. So if you go back to the process described in a HS chart or a TS chart, so 3 dash to 2 dash is the compressor process and 4 to 5 dash is the turbine process. So this should be equal. So Cp T3 dash minus T2 dash is the compressor work equals Cp T4 minus T5 dash. So from this I can estimate the temperature at the exit of the turbine. So T3 dash minus T2 dash plus equals T4 minus T5 dash. So T5 dash will be 1383. This is the turbine inlet temperature minus your change temperature in the compressor. So Cp, because Cp gets cancelled because both are same, so this becomes 1171.8 Kelvin. So basically my temperature drop across compressor is equal to the temperature drop across the turbine. So this is for the actual case. So T4, I need to find out T5 dash is the actual temperature at the exit. So if it was an isentropic process, then I would have get T5. So this is actual. I need to find out isentropic, so that I can get it from the turbine efficiency. I need to find out this temperature, isentropic temperature, to find out the pressure ratio across the turbine. So I know the exit pressure. I have now found out the inlet pressure to the turbine, so I have to find out the exit pressure. So for that I need the temperature. So then I can assume that it's an isentropic pressure. I can estimate the pressure at the exit. So T5, the turbine efficiency is my actual divided by ideal. So T4 minus T5 dash divided by T4 minus T5. So rearranging it, it will become T5 equals T4 minus T5 dash divided by the turbine efficiency. So substituting the values, so T4 is 1383 minus, so 1383 minus 1171.8 divided by 0.8. This comes out to be 1119 Kelvin. So now I know the isentropic temperature if the process was isentropic across the turbine. Then hello,
ஹலோ
சொல்லுடி. நெல்லிக்காய் வாங்கலை. So the temperature for an isentropic process, then T4 by P5 equals P4 by P5 raised to power gamma minus 1 by gamma. I know P4, which is 5.88, and I need to find out P5. So and I know the temperature, substituting that, so 1383 by 1119 by raised to power 3.5 equals 5.88 divided by P5. So using this I can estimate the pressure at the exit of the turbine as 2.8 bar. You see, 0.78 was the inlet. It was compressed by, because of ram effect, to 1.044, and then it was compressed to 5.8 times of that, and then it was expanded to 2.8 bar, and then it again is expanded to ambient pressure in the nozzle. So now T5 dash by I know P5. So now I have to estimate the exit condition in the nozzle. So to do that, I assume that in the nozzle is an isentropic process. So again T5 dash by T6 equals P5 by P6 raised to power gamma minus 1 by gamma. So this will become 2.8 by 0.78 raised to power 1.4 by 1.4. So this is equal to 1.44. So T6 is T5 dash by 1.44, which is 1171.8 divided by 1.44. So this comes out to be 813.75 Kelvin. So this is assuming it's an isentropic process. Now the nozzle efficiency is given. So nozzle efficiency is the actual divided by ideal. So actual is T5 dash minus T6 dash divided by T5 dash minus T6. So from this we can find out T6 dash as T6 dash equals T5 dash minus the nozzle efficiency raised to power into T5 dash minus T6. So substituting the temperature, my actual exit temperature is 849.5 Kelvin. So now I know the temperature to the exit. So using that I know the inlet condition and the exit condition. So I can estimate the velocity at the exit. So velocity is 44.72 into your enthalpy change across the root of 2 times, so 2 into 1000, so that's taking out, it will become 44.72. So 44.72 into root of my enthalpy change across the nozzle. So nozzle process is 5 dash to 6 dash actual. So expressing in terms of temperature, it becomes Cp into T5 dash minus T6 dash. So here the enthalpy changes in kilojoule per kg. So it becomes 44.72 into root of 1.005 into my temperature 1171.8, which is T5 dash, minus the exit temperature 849.5. So with this I can find out the exit velocity of jet is 804.8 meters per second. So the specific thrust will be, so 1 plus mf into my jet velocity, which is equal to 1 plus mf by ma. So 1 plus 1 by 48.34 into 804.8. So that is 821.45 Newton per kg of air per second. Now I need to find out the total thrust. So the volume of air flowing is, so diffuser is cross section area is given. So V1 is 0.12 into 216, so 92 meter cube per second. So mass flow is PV by RT. So pressure is 0.78 bar into 10 power 5. So converting to Pascal into volume we have found out. Which is 92 meter cube per second, divided by R. So 0.287 divided by into 1000 into 265.8. So this gives me 26.5 kg per second. So total thrust will be 26.5 into 821.45 Newton per kg, in the specific thrust. So this becomes 21768.4 Newton. Specific thrust is thrust divided by the mass of air. So moving on to the next question. So the following data pertain to a turbojet flying at an altitude of 9500 meter. The speed of the turbojet is 800 km per hour. The propulsive efficiency is 55%. The overall efficiency of the turbine plant is 17%. The density of air at 9500 meter altitude is 0.17 kg per meter cube. So the drag on the plane is 6100 Newton. Assuming calorific value of the fuel used as 46,000 kilojoule per kg, calculate first absolute velocity of the jet, 2 volume of air compressed per minute, 3 diameter of the jet, 4 power output of the unit, and 5th air fuel ratio. So again now there are multiple things given. So we have propulsive efficiency is given, the speed of the turbojet is given, my overall efficiency is given, and the density is given, the calorific value is given, and the drag, which is the resistive force acting on the plane, is given. So with this we'll see. So what is known? So altitude 9500 meter, and the absolute velocity of the jet CA is 800 km per hour. So converting that into meters per second, so 800 into 1000 divided by 3600. So that comes out to be 222.2 meters per second. So that is the velocity of the air which is coming in, or the velocity of the aircraft. Then the propulsive efficiency is given, which is 55%, and the overall efficiency is 17%, and drag is 6.1 kilonewton. So first is we need to find out the absolute velocity of the jet, which is Cj minus Ca. So the propulsive efficiency is nothing but 0.55 percent, 55%, so 0.55. So propulsive efficiency is given as 2 times the aircraft velocity divided by the jet velocity plus the aircraft velocity. So substituting the aircraft velocity and propulsive efficiency, we can find out the jet velocity. So 0.55 equals 2 times 222.2 divided by the jet velocity plus 222.2. So rearranging it, it will become 2 times my jet velocity divided by the propulsive efficiency 0.55 minus the jet velocity, aircraft velocity. This comes out to be 585.8 meters per second. So that is my exit velocity of the jet. So the absolute velocity is the difference Cj minus Ca. So this comes out to be 363.6 meters per second. Next is the volume of air compressed per minute. So for this, the propulsive force is m dot A into Cj minus Ca. So this will be equal to the drag force. So 6100 into my so because the aircraft is moving in a constant velocity, so there is no forces acting. So whatever force thrust is generated is equated by the thrust. Thrust is equated by the drag force. So the propulsive force is equal to the drag force. So the propulsive force of the thrust is mass into the velocity change, so the absolute velocity. So m dot A into your difference in velocity equals your drag force 6100 kilonewton Newton. So from this, the air mass of air flow rate is 6100 divided by 585.8 minus 222.2, or the absolute velocity which you have found out 363.6. This comes out to be 16.77 kg per second. So the value of volume of air compressed per minute is 16.77 divided by 0.17 into 60. So this gives 5918.8 kg per minute. So mass by density is your volume. So with this I have found out the volume. Next is we need to find out the diameter of the jet. So for that, I know the exit velocity, and the cross sectional area into velocity gives me the volume flow rate. So the volume flow rate is 5918.8, which you have found out, equals pi by 4 d square into jet velocity. So substituting that, I have to convert this volume flow rate into meter cube per kg, meter cube per second. So this unit is around 5918.8 meter cube per second minute. So divide by 60. So d becomes 5918.8 into 8 into 4 divided by 60 into pi into your velocity 585.8 raised to power half. So this comes out to be 0.463 meter or 463 millimeter. So diameter of the jet is 463 millimeter. So sorry, in the previous question here the thrust we have to find out the difference in velocity, so Cj minus Ca, so that is not added, so please include that. So I have found out the diameter, which is 463 mm. So next is I need to find out the power output and the air fuel ratio. So power output is nothing but thrust power equals drag force into velocity. So thrust power will be your drag force or the thrust which is acting, so 6100 into velocity 222.2 Newton per meter per second. So divide by 1000 to convert it into kilowatt. So this gives me 1355.4 kilowatt. So the turbine output will be my thrust power divided by a propulsive efficiency. So 1355.4 divided by 0.55 will give me 2464.4 kilowatt. So with that I can find out my turbine output. Next is overall efficiency. So overall efficiency is heat equivalent of output divided by my heat input. So here we need to use the change in kinetic energy divided by mass of fuel into calorific value. So that will come out to be, with that I can find out mass of fuel as 0.315 kg per second. So air fuel ratio is air used divided by fuel used. So it will come out to be 53.24. So here we need to use the change in kinetic energy. So here see thrust work divided by heat supplied by fuel. So Cj minus Ca into Ca. So that's what we have to use. So here it will be Cj minus Ca into Ca. This is the thrust power, which is 1355.4 kilowatt. So this will be thrust power divided by mass of fuel into calorific value. So next is in a jet propulsion unit, air is drawn into the rotary compressor at 15 degrees Celsius and 1.01 bar and delivered at 4.04 bar. The isentropic efficiency of the compressor is 82% and the compression is uncooled. So after delivery the air is heated at constant pressure until the temperature reaches 750 degrees Celsius. The air then passes through a turbine unit which drives the compressor only and has an isentropic efficiency of 78% before passing through the nozzle and expanding to the atmosphere pressure of 1.01 bar with an efficiency of 88%. So neglecting any mass increase due to the weight of the fuel and assuming that R and gamma are unchanged by combustion, determine the power required to drive the compressor. The air fuel ratio of the fuel has a calorific value of 42,000 kJ per kg, the pressure of the gas leaving the turbine, the thrust per kg of air per second. Neglect any effect of the velocity approach, assume R and gamma value is given. So same jet propulsion, we have rotary compressor, inlet pressures and outlet pressure is given, temperature is given. So isentropic efficiency of the compression is given. So after delivery, here the inlet temperature to the turbine is given, the efficiency of turbine is given, and also nozzle efficiency is given. So this is how the process looks. So 1 to 2 dash is the actual compression and 3 to 4 dash is the actual turbine expansion and 4 dash to 5 dash is the nozzle expansion. So what is known? So T1 is 4288 Kelvin and P1 is 1.01 bar. So P2 is 4.04 bar which is given. So the compression ratio is 4 and T3 inlet to the turbine is 750 degrees Celsius, so 1023 Kelvin, and your compressor, turbine and nozzle efficiencies are given. So referring to this figure, so assuming the compression is an isentropic process, So T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. So substituting that, T2 by T1 will be 1.486. So with that I can estimate the temperature at the exit of the compressor, which is 428 Kelvin. So compressor efficiency is now T2 minus T1 by T2 dash minus T1 dash. So and compressor efficiency is given as 0.82. So T2 actual ideal by actual for compressor. So T2 dash is 458.7 Kelvin. So Cp is R into gamma minus 1 by gamma minus 1. So R is given as 0.287. So Cp will be 1.004 kilojoule per kg Kelvin. So first is we need to find out the power required to drive the compressor. So which is Cp T2 dash minus T1. So that is change in enthalpy. So this comes out to be 171.38 kilowatt, and air fuel ratio is so applying an energy balance across the combustion chamber. So M of into C equals Ma plus Mf into Cp into the change across the compressor combustion chamber, which is T3 minus T2 dash. So or else you can change here Ma plus Mf is taken together, or else you can take inlet and exit stream, just like what we did in the previous problem. It will also give you the approximately same values. So air fuel ratio will be Ma equals Mf into C divided by Cp into T3 minus T2 dash minus Mf. So Ma is 42000 divided by 1.004 1023 minus 458.7 minus 1, which is 73.1. So air fuel ratio is 73.1 is to 1. Next is pressure of the gas leaving the turbine. So actual turbine work equals actual compressor work. So with that we can equate the works. So Cp T2 dash minus T1 equals Cp T3 minus T4 dash. So only unknown is T4 dash here. So substituting the other temperatures, so T4 dash comes out to be 852.3 Kelvin. So turbine efficiency is my actual by ideal. So T3 minus T4 dash divided by 3 minus T4. So turbine efficiency is 0.78. So substituting the temperature, I can estimate the isentropic temperature if the process is isentropic. So T4 is becomes 804 Kelvin. So now T4 by T3 is because T3 and T4 is the isentropic process work temperature. So assuming isentropic process, T4 by T3 equals P4 by P3 raised to power gamma minus 1 by gamma. So with this I can find out the pressure ratio. The P4 by P3 is 0.43, and I know the inlet pressure, so I can find out the exit pressure, which is 1.74 bar. Next is we need to find out the thrust per kg of air per second. So T4 by T5 equals P4 by P5 raised to power gamma minus 1 by gamma. So 1.74 by 1.01 raised to power 1.4 minus 1 maybe 1.4. So this comes out to be 1.168. So the ideal temperature is 729.7 using the nozzle efficiency. So it's actual very ideal. So T4 dash minus T5 dash divided by T4 dash minus T5. So this comes out to be nozzle efficiency is 0.88. So T5 dash is 744.4 Kelvin. So the actual temperature is 744.4 Kelvin. So with this I can find out the jet velocity. So jet velocity is Cj square by 2 equals Cp into your change in temperature across the nozzle, T4 dash minus T5 dash. So Cj is root of 2 into Cp into T4 dash minus T5 dash. Substituting the temperature and converting it to joules, so it becomes 465.45 meters per second. So the thrust per kg per second is 1 into 465.5. So assuming inlet is 0, so it will be 465.5. So 465.5 Newton. So Next two problems are left. So air at 7 degrees Celsius enters a turbojet engine at a rate of 16 kg per second and at a velocity of 300 meters per second. Air is heated in the combustion chamber at a rate of 15,000 kilojoule per second and it leaves the engine at 427 degrees Celsius. So determine the thrust produced by this turbojet engine. So we need to find out the thrust. So if we apply an energy balance across the whole engine, so we assume the aircraft is stationary and the air is moving towards the aircraft at a velocity of 300 meters per second. So taking the entire engine as our control volume and writing the steady flow energy balance equation. So this is my engine. So I am applying an control volume here across the engine. So my inlet is coming at 70 Celsius, 300 meters per second, and mass flow rate is 16 kg per second, and going out at temperature of 427 degrees Celsius. My inlet heat is 15,000 kilojoule per second. So T1, the inlet temperature for this, the enthalpy is 280.13 kilojoule per kg from the air standard table. So you can see, and my enthalpy out is 713.27 kilojoule per kg. My pressures are same, both inlet and outlet. My pressures will be same. So assuming that ambient pressure. So E in minus E out is the change in energy, because it is steady process, steady state process. So energy in is equal to energy out. So Q in plus inlet enthalpy plus kinetic energy of the fluid equals the inlet exit enthalpy and kinetic energy of the fluid. So Q in equals m dot into H2 minus H1 plus V2 square minus V1 square by 2. So with this, substituting all the values, you can find out the exit velocity. So exit velocity will come out to be 1048 meters per second. So with this, I can find out the thrust. Fp is mass into change in velocity. So 16 kg per second into inlet exit velocity 1048 minus inlet is 300. So this comes out to be 11,968 Newton. Next, final question. A turbojet aircraft flies with a velocity of 1100 km per hour at an altitude where the air temperature and pressure are minus 35 degrees Celsius and 40 kilopascal. Air leaves the diffuser at 50 kilopascal at a velocity of 15 meters per second. So turbojet inlet starting is your turbojet. So the exit condition of the turbojet is given. Inlet to the turbojet is also given. So inlet is at minus 35 degrees Celsius and 40 kilopascal, and the inlet is the turbojet velocity 1100 km per hour. They are saying that it's leaving the diffuser at 50 kilopascal and at a velocity of 15 meters per second. And combustion gases enter the turbine at 450 kilopascal and 950 degrees Celsius. So that is your exit to the compressor. So it is at 450 kilopascal, that is 4.5 bar and 950 degrees Celsius. The turbine produces 800 kilowatt of power, all of which is used to drive the compressor. So assuming an isentropic efficiency of 83% for the compressor turbine and nozzle, and using variable specific heat. So we need to use a table. So determine the pressure of combustion gas at the turbine exit, the mass flow rate of air through the compressor, the velocity of the gases at the nozzle exit, and the propulsive power and the propulsive efficiency of this engine. So T1 is minus 35 and pressure of 40 kilopascal. So from the table we will find out enthalpy is 238.36 kilojoule per kg. So across the diffuser, if you apply an energy balance, it will be H1 plus V1 square by 2 equals H2 plus V2 square by 2. So substituting the values here, my inlet velocity is 1100 divided by 3.6. So 1100 into 1000 by 3600. So that's what is given. And the inlet enthalpy is 238.36. Gives H2 plus my exit velocity of the turbine is given. So substituting that, it's 284.93 kilojoule per kg. So H2 is 284.93 kilojoule per kg, and the pressure is also given as 50 kilopascal. So using that, I can find out the entropy is 5.8513 kilojoule per kg Kelvin. So entropy at the exit is known. So the compressor process 2 to 3. So P3 is 450 kilopascal, and assuming that's an isentropic process, so the actual ideal enthalpy is 534.42 kilojoule per kg. That is the ideal enthalpy. So because the compressor is not 100% efficient, so compressor efficiency is H3 dash minus H2 divided by H3 minus H2, ideal by actual. So 0.83 is the compressor efficiency, so divide equals substituting the enthalpy values, I can find out the actual enthalpy at the exit of the compressor, which comes out to be 585.52 kilojoule per kg. Similarly, hello, முடிய போய் வரேன்டி ஏறி முடியலடி. So I know that the whatever work is generated in the turbine is getting utilized in compressing the fluid in the compressor. So the change in enthalpy across the turbine is equals to change in enthalpy across the compressor. So H3 minus H2 equals H4 minus H5. Also I know the inlet to the combustion, the inlet to the turbine is known, which is 450 kilopascal and 950 degrees Celsius. So correspondingly that enthalpy is 1305.2 kilojoule per kg. So with this, substituting the values here, H3 minus H2 equals H4 minus H5, we can find out the enthalpy exit to the turbine, which comes out to be 1004.6 kilojoule per kg. So also the turbine efficiency is known. So turbine efficiency H4 minus H5 divided by H4 minus H5s. So with this I can find out the ideal enthalpy which at the turbine exit when the turbine is in isentropic process. So enthalpy at the exit of the turbine when it follows an isentropic process is 943.04 kilojoule per kg. So since I can find out assuming it's an isentropic process, so inlet entropy is from the temperature and pressure, you can find out inlet entropy is 6.7725 kilojoule per kg Kelvin. So at the turbine exit, assuming it's an isentropic process, so I know entropy and enthalpy, I can estimate the pressure. So P5 is 136.9 kilopascal. So now the mass flow rate of air through the compressor is your compressor work divided by the enthalpy change, or similarly H3 minus H2, or your enthalpy change across the turbine. So 800 divided by the enthalpy change becomes 2.661 kg per second. So across the nozzle, the inlet enthalpy is 1004.6 kilojoule per kg and pressure is known 136.9 kilopascal. So correspondingly the entropy is 6.8382 kilojoule per kg Kelvin. So and exit is the ambient pressure. So corresponding to this enthalpy, entropy and pressure, my enthalpy is 6713.12 kilojoule per kg if the process is isentropic across the nozzle, but the nozzle efficiency is given as 0.83. So the actual by ideal. So with that I can find out the actual enthalpy at the exit of the nozzle, which comes out to be 762.68 kilojoule per kg. So doing an energy balance across the nozzle, I can find out the exit velocity. So exit velocity is again root 2 into enthalpy change. It comes out to be 695.6 meters per second. So with this I can find out the propulsive power. So propulsive power is mass into your velocity change into the inlet velocity. So V6 minus, that is thrust into the inlet velocity. So substituting the velocities in the mass flow rate, I will get 317.2 kilowatt. So this is the propulsive power, and the Q in is m dot into H4 minus H3. So that comes out to be 1915 kilowatt. So propulsive efficiency is per propulsive power divided by the heat added. So that comes out to be 16.6%. If it was overall, then it will be divided by the calorific value because of the combustion. So the propulsive efficiency of this engine is 16.6%. So with that, we have finished the topics covering the aircraft propulsion engines and the Britons and gas power cycles. So next week we'll look at on refrigeration and psychometrics. So with that we'll end this today's session. So Thank you.